All right, let's keep on keeping on with limits. In section 2.2, we're going to talk about the definitions of limits. So basically today what we're going to do is say, all right, now we have the general idea where you take that average velocity or that secant and you work in towards an instantaneous. We're going to see what that looks like on a graph. That's what our plan is for today. But first, let's lay out what our actual definition is. And I think it's important sometimes to write out definitions. Now, I don't expect you to memorize definitions. I do want you to have a good working knowledge of these concepts, but sometimes it's good to look at the mathy way of doing this stuff so that you can actually see what up. All right? So here's the definition of a limit of a function. Okay, so suppose the function f is defined for all x near a, except possibly at a. That's a big deal. If this f of x is arbitrarily close to L, as close to L as we like. For all x sufficiently close but not equal to a, we write. I'm going to squeeze this in. And then here's the gold, people. Here's the notation. The limit as x approaches a of f of x equals L. And we say, let me scoot this down. I got this up here too close. And we say the limit of f of x as x approaches a equals L. Okay, get that written down. You can even pause the video here if you need to write that down a little bit more. And then we'll come back to it. All right, then hit play when you're ready again. Here's the deal. Suppose that we have this function f that's defined for all x near a except possibly at a. When you have a limit, you do not have to have a value. Ooh, that's big, right? So when you have a limit, you're looking at the behavior of what's happening, what it is approaching. You don't necessarily have to have an actual value there. You just want to know what is right here, arbitrarily close. So as close as you can possibly be. That's what you're looking for. For all x sufficiently close but not equal to a, we write this limit notation. Learn it, love it, because it sticks with you forever. The limit as x approaches a of f of x equals L. All right? Okay, now let's get some visual representation associated with that. So here is example 1. Let me make this a little bit bigger here because we're going to be looking at this graph. Here's example, oh, that's not helpful. Here's example 1. We're going to use this graph to determine these limits. Find the values. Here is A. I want to figure out what is f of 1. So at 1, what is the value of my function at 1? 2. Good. Now, what is the limit as x approaches 1 of this function? So what I'm actually doing here is I'm saying As my graph approaches from the left and from the right, we'll talk about that more. What is the value of my function that my graph is going toward? Still 2. It's okay to have your limit and your value be the same thing. Look what happens when we talk about this next part. What is f of 2? Yeah, it's all the way up here at 5, right? That's my dot. That's my filled in value. That is this a piecewise situation. At 2, the value of my function is 5. But what about the limit? As I approach 2, where does my graph approach? 3. Do I have a value at 3? No. But my graph is still approaching 3, right? That, ladies and gentlemen, is the concept of a limit. What is my graph approaching? What does it appear to be going toward? That is the kicker of a limit. So my limit is 3. You do not have to have the same value for, make this a different color, for your function as you do for the limit. That is not how limits work. So you got to get out of your head a little bit. I know up to this point, it's been very rigid. Plug this in, get this value. Now you're going to have to think outside the box a little bit. You're going to have to expand that little noggin of yours, think outside the box and see, what am I approaching? What is this going toward? Not necessarily just a plug and play. Cool, right? All right, check this out. What if I have f of 3? Nothing. There is no value at 3. This does not exist. I have no value at 3. DNE means does not exist. Undefined. Either way is fine. I don't care what you write. What if I have my limit as x approaches 3? That does exist. And it is a 4. Cool, right? I'm letting that soak in. So when I'm looking at a limit, you don't necessarily have to have a value of your function at that point. It's just, what is my graph approaching? And that is the concept of a limit.